Mr. Zois ASIMAKOPOULOS. Mr. ASIMAKOPOULOS is a mechanical engineer. He is currently working in PANTEC SA and collaborating externally with the Public Power Corporation SA. I would like to tell now that from now on we're going to have short presentations because we're going to present you posters of this meeting.
Hi everyone. I'm Zois ASIMAKOPOULOS, a mechanical engineer, and I'm here to present you some work from the thesis which I do with Mr. Panaras at the Hellenic Open University. I would like to thank also the Greek chapter of ASHRAE for giving me this opportunity to be here and discuss my thesis. And also the Hellenic Open University, which also established a student chapter this year. So the topic of my thesis is the assessment of smart readiness, smart technologies in Greek buildings through the Smart Readiness Indicator. The Smart Readiness Indicator, or simply SRI, as an official definition, was introduced in the European Directive in 2018. On the energy, in this directive, the EU highlighted the importance of digitalization systems in the building stock and defined the SRI as an indicator that could assess the ability of buildings to integrate smart technologies into them. Since 2020, the SRI has been running as a pilot process in many EU members, and this day it remains a voluntary system. About the methodology, I will say something about the methodology and I will show you some results from this work. About the methodology, okay. There are identified 9 technical domains in the SRI, which is heating, cooling, ventilation, domestic water, etc. And the first thing that we do in the work is when we identify which technical domain are installed in the building or building unit we study. The options are that the domain exists in the building, so we evaluate it, or is absent, but we should evaluate it because, for example, the ventilation we should have in some buildings, in some sectors, or that is absent and there is no requirement to evaluate this domain. Once we identify the domains, we ask to choose one of the 2 methods, A or B. These methods relate to the number of services that we see and we evaluate. By service, by the word service, we refer to general functions provided by the technical systems, such as the ability to control heat emissions, control distribution networks, control air supply, and more. Each service studied has specific level of functionality, and thus is intelligence in the way it operates. For example, in the service of controlling heat emissions in a heating system, there may be maybe we have a thermostat for an entire thermal zone which shows no technological intelligence according to today's standards. Or there may be multiple smart thermostats installed in different parts of thermal zone which can communicate with each other and activate only upon detecting presence. Similarly, for ventilation, the service of controlling air supply may involve a central ventilation system, or it could be a system that activates depending on the CO2 levels in each room. The more advanced the functionality levels in each service, the smarter the service becomes. The definitions of these functionality levels plays a crucial role in the impact criteria. The impact criteria are 7: energy performance, comfort, convenience, user information, etc. These are these are linked to the technical domains and their intelligence level. A highly advanced technical domain can provide high score in the associated impact criteria. For example, a smart heating cooling system with detectors, machine learning, etc. will affect user comfort and health and will play a key role in informing users about when and how they consume energy for heating. Similarly, a good control and monitoring system will score well in the maintenance and fault prediction impact criteria. Optimizing energy performance. All these impact criteria interact with the three key functionalities: energy savings, operational efficiency, user needs satisfaction, energy flexibility. The way that these interact is in the methodology that provided from the EU. In this thesis, we have about 10 or 12 buildings from the PPC group that we researched about what is the consumption, energy consumption, what system, HVAC system are installed there, and after that we see the SRI, we calculate the SRI. So we had, until now, I have two results to present you, the building A, the building B. The building A is in the climate zone D, here in northern Greece. Our construction year is 1983. Is renovated the 2023. Has a VRF HVAC system, and the EPC class is B. About the building B is an office building that we make the EPC performance, and we see that the class is B+. So we collect the domains that installed in this building, and we calculate the SRI results. From this work until now, we see that the building A, which has EPC class B, has way more SRI score, and that is because of maybe VRF system. And the building B, for example, that we don't have a ventilation system or we have split units, but we have B+, and we have greater score of SRI. We want, with this work, to evaluate more buildings in order to see how the SRI scores and the EPC class interact one with each other, and make some results that we can collect and inform the users and the group, PPC group that we're working at. Thank you very much.